I think that's better.
I think it is better in the long run, but I think it is better in the long run, but it's a little daunting.
Yeah,
It's okay.
I agree. So what fixation are you using? Are you gonna use like only equations, like potential flow?
No, I actually use the aerospan or the aero buildup method. I actually have to ask you why. The old code just uses equations, and it like manually estimates the data, which I think is pretty stupid. So I want to use aero buildup on the actual SN model.
Okay, good morning everybody. So I see our number stabilizes at around 25. I think it's a very good number for us to actually have a small enough class for us to interact in the classroom and in the lab sessions. So if you didn't get the announcement, we're going to have a wind tunnel tour this afternoon. So we'll meet in this room, 2 identical sessions. So you can come either at 1 o'clock or 2 o'clock. And we're going to have a brief introduction and then head downstairs to the Wright Brothers wind tunnel and for you to have a tour of the facilities. And what is unique about the wind tunnel we're going to introduce. All right. And so today we're going to continue on the fundamental concepts, understanding aerodynamic forces, and we'll lead into flow kinematics and vorticity. All right. And so here's a tentative schedule. So today is the second class. We'll be talking about lift and the vortices, and the different colors are different parts of the class. We'll have a potential flow over here, like inviscid flow over here, viscous flow and the compressible flow, and then there is project work. All right, so you can find the tentative schedule on the OneNote. All right, the labs are going to be 1 to 2 and 2 to 3, right? According to our survey, that seems to be the best 2 spots that fits everybody's schedule. And the office hours, the fixed one is going to be Monday from noon to 1 p.m. That seems to be fit most people's schedule. And for those who can't, I'll have office hours, maybe alternative weeks on Wednesdays. And I'll also be online a lot of the time. All right. Okay, so we'll dive into this lecture on aerodynamics, the science of manipulating fluid that you cannot see, you can almost not feel, but is everywhere, right? And there is nothing like the thorough understanding of aerodynamics that immediately qualifies you as an aerospace engineer. So let's go ahead. And in the last lecture, we talked about a lot of applications of aerodynamic forces. I just want to reinforce the concept, especially the concept that we use lift a lot more than we use drag. Another example is what actually turns a ship, right? A ship is, especially large ships, are very heavy, very massive things. And what actually turns it, makes it change direction? Again, it's lift forces, right? It's actually lift forces from 2 different sources, right? There is one lift source that changes its orientation and another lift force that changes its velocity. And the 2 lift forces are actually in opposite directions. Why? So first of all, let's look at the rudder. Okay, if the ship wants to turn left, what force has to be exerted on the rudder for it to actually change its orientation towards the left? It has to be a lift force towards the right side, right? And there has been a lot of calculations on the rudder to figure out what kind of rudder is the best. And it's actually very common for rudders to take a NACA airfoil, right? It's basically kind of a standard rudders are symmetric NACA airfoils. There is another lift force on the ship itself, right? After the ship has changed orientation, it basically has an angle of attack relative to the water. and it's the angle of attack that makes, if it wants to turn left, then the angle of attack is going to induce a leftward lift force on the majority of the ship that actually changes its direction, that provides the centripetal force for the ship to actually turn. Okay, so next time if you want to explain why the Titanic sank, it did not have enough lift forces. All right, so similarly, like a lot of people, I think at MIT there is a free sailing program for you to learn how to sail, right? And what forces propel, not just the turns, but also propels a sailboat? It's the lift forces. It's actually a combination of the lift force on the sail and the lift force on the keel, so on the hull of the boat. And in this case, it's the combination of a lift force on the sail and the lift force on the hydrofoil, right, that propels the sailboat. The fact is that the wind, the air, and water have a relative velocity. And as a result, the relative velocity of the boat to the air compared to the relative velocity of the boat to the water has a different vector. Okay? As a result, the lift forces also has an angle. Is the misalignment of the two lift forces, right? The sum of the two vectors that provides the propelling force that counteracts the drag on the boat. So there has been a lot of, again, calculations, for example, like on the sail. The sail is basically a wing. Just instead of like the last lecture we looked at the wing of a car, it provides a lift downward. The sail basically provides a lift sideways, right? That's how a sail works. So now one of the questions we want to answer today is why we use lift a lot more than drag. In fact, an average Joe walking on the street knows probably how to use drag forces, right? I mean, if you are in water, you want to propel yourself, even if you don't know how to swim, you are like using drag forces, right, to push yourself. But an aerodynamicist knows how to use lift forces. And why is lift forces more useful, more efficient than drag forces? And to understand that, you need to not just look at the solid, but also look at the fluid, look at the air. How much energy does it cost to generate, let's say, the same amount of lift versus drag? And to understand that, you need to understand conservation, right? Conservation of energy, conservation of momentum. That's something we'll look at today, right? So in unified fluids, you probably either excelled or suffered from control volume analysis, right? Looking at what is the momentum flux, what is the energy flux, and today we're going to review that and partly explain why it is more efficient to use lift. And something we'll look at today is actually a prelude of a lot of what we'll go through in the semester. That is, for example, if you look at lift, there is no simple explanation of why airplane flies. So if somebody tells you, I have a simple theory of why lift exists, he's probably wrong. So there is a lot of different angles to look at why airplanes can fly, why there is lift. And through the course of the semester, we'll kind of zoom in. We'll take a zoom in kind of perspective. We'll look at the whole airplane first, okay? And explain in that angle of view, right, from a macroscopic point of view, why the airplane generates lift, right? Why the airplane induces or moves air in a downward direction so that it gets a counteracting force in the upward direction. So that's kind of an overall taking a macroscopic view. And then we'll zoom in a little bit more into the wing, right, and figure out, okay, why does the wing actually is able to induce a downward velocity, right? And further and further, and into the boundary layer and things like that. So here we'll take an extreme macroscopic point of view and see why it is more energy efficient to use lift. So if you take an object that generates majority of the aerodynamic forces through drag, an example is a bluff body like that, right? And a bluff body like that essentially has a sharp angle over here and over here that creates a almost a surely location for flow separation. And we'll talk more about flow separation later on, especially flow separation around the not sharp angles but smooth objects. But it is actually intuitive, right, for flow to separate around the sharp angles like that, right? And we'll look into why that is the case later when we look at boundary layers. But for now, it is sufficient to know once you have a sharp edge, right, the flow separates. Now, in the flow separation zone, there is a lot of random vortices, turbulence, which we'll talk about very late in the semester. But for now, it is sufficient to know that the velocity in the separation zone relative to the solid body is much lower than the free stream velocity. Let's say V infinity is the flow velocity. So when you look at a control volume like that, and in particular, if you think about the control volume and think about the energy that goes into the control volume and out of the control volume from the frame of reference of the ground, so ground reference, then the velocity that goes into the control volume, right? The energy, the kinetic energy that goes into the control volume is not surprisingly zero, because we are taking the ground reference. The velocity that goes into the control volume is zero relative to the ground, right? So we are thinking about this object moving in the forward direction. So this object is moving and the ground is stationary relative to the air. Okay, so the energy flux, so energy in is equal to zero. How about the energy flux out of the control volume over here? Well, the energy that comes out is also zero over here and zero over here, because the air is not disturbed, right, outside of the separation zone. But the air has a forward velocity in the separation zone. So there is a lot of energy that is almost, so the velocity, the energy per mass of air is approximately equal. The reason is approximately equal is because the velocity is not exactly equal to the velocity of the solid body, but approximately equal. So half of V infinity squared, right? So basically, to generate drag, you have to dump energy into the flow. There is energy, there is a moving air particles that is trailing behind you. So that is true for anything that has a drag. Even very streamlined bodies, it will have a boundary layer, and as the boundary layer goes behind the body, there is going to be a narrow wake, viscous wake, right? It's going to be much smaller than this, but there is going to be energy that is dumped into the air that is dragged alongside the body to move with roughly the velocity of the body. Now let's look at lift. Again, let's draw a control volume, right? Let's draw a control volume. Screen. Okay, and in particular, let's look at an airfoil of infinite span. The reason we are looking at infinite span is we're not considering induced drag for now, right? For something, an airfoil of infinite span or very long span, what happens is the inflow has a zero velocity relative to the ground. So zero energy goes in and zero energy goes out, right? So if you neglect the viscous layer near the body, then the air upstream of the airfoil and downstream of the airfoil are not moving at all. So as a result of that, while generating lift, you are not really dumping any energy into the air at all. That gives you the maximum possible efficiency. Okay, so one of the homework you're going to be doing this week is I want you to analyze an example of using lift versus drag. So this is a rowing stroke. So if you look at the slow motion of somebody rowing, so let's actually focus on the relative motion between the oar and the water. So just look at what is the relative motion between the oar and the water. Just think about the water is actually moving that way, right, relative to the boat. And the relative motion between the oar and water is actually not obvious. Gravity, just look at the flowing water. It looks like the oar is almost moving together with the water. But the relative motion, it is not obvious. It's either streamlined or sideways. So there is a lot of analysis on rowing that shows that the oar actually doesn't really work by drag, but works by a combination of lift and drag. And to make the analysis easier, the homework is just to think about two extreme scenarios. Suppose the oar propels the boat by pure drag, assuming it has no lift at all. Which means you have to assume the relative motion, right, between the oar and water is exactly in the direction of the force which propels the boat, right, in the direction of the motion. So if that is the case, compute how much mechanical power, right, has to input into the oar, which is the power output of the person rowing, right, and compute what is the energy efficiency. Basically, what is the ratio of useful work, the velocity times thrust, right, to the input mechanical power. And how does that depend on the velocity of the boat, the area of the oar, and the thrust required, right? That's assuming a drag coefficient of 1, and also assuming a lift coefficient of 1 in the second question, assuming the oar is purely propelled by lift. What that means is that the relative motion between the oar and water is in the perpendicular direction, right? If you think about the oar stroke, it kind of moves out and then in, right, in the water. So assume it is purely perpendicular. Calculate again how much power does it require and how much efficiency you get. And by doing the homework, I hope you start to understand why we use the lift a lot more than drag, especially in applications where efficiency is important, like energy efficiency is important. All right, any questions on that? Yes?
Yeah, the scenario where you said, on the diagram where you said that there is no energy transfer to the air in the only lift scenario. We didn't consider the boundaries up and down. So
that's right.
So how do you know that there is no energy in the air, like, or more air going, energy changing the air, like changing its direction, going up or going down, or?
That's a very good question. So basically the question is, how do we know that by generating lift in the previous example, the air particles are not disturbed, right? That is why we are saying we are taking a macroscopic point of view, right? In the macroscopic point of view, the air is basically going in the same direction, upstream and downstream. Of course, when you zoom in, there are particles that moves either upstream or maybe even downstream or sideways. So we'll analyze that more and more in the next few lectures, right? And in the next part of the class. But from a macroscopic point of view, the air downstream has no reason to move either direction. Okay, it is basically on average, it is still not disturbed. Okay, so actually immediately in later this class, we are going to see that it is not entirely the case. It is not entirely has zero velocity, but it does have a reason to move in the opposite direction of the lift, right? And we'll look exactly how much it has to move in the opposite direction of the lift, and that's related to induced drag. So any reason the air moves downstream, right, is going to mean that the air now has energy, right? That the fact that the air has energy means there has to be some kind of power input to the air, and that means there has to be some form of drag. And the different form of drag exactly coincide with different reasons the air has to move downstream of the lifting device. So we'll talk about that. Okay, so to understand a little bit more on the lift forces, let's actually watch a video. And I just want you to focus not just on Tom Cruise, but on what not on what the airplane is doing, but on what the air is doing around and behind the airplane. So let's take a look.
Who the hell is that?
Maverick to range control. Entering point Alpha. Confirm green range.
Maverick, range control. Green range is confirmed. I don't see an event scheduled for you, sir.
Well, I'm going anyway.
Nice.
Setting time to target, 2 minutes, 15 seconds.
2:15, that's impossible.
Final attack point. Maverick's inbound.
I'll stop over here and yeah, so most of the time you actually can't see the air, right, as usual. And one of the things I want to ask you is there is a lot of aggressive turning over here. What is providing the centripetal force for the turns? Lift again, right? So in this case, actually, the for a fighter airplane like this, the most powerful lift is not really providing counteracting gravity, right? But providing the centripetal force for the turning, which is usually multiple times of the gravitational acceleration. And in particularly, this is actually a very rare scenario. We can actually visualize the air around the airplane, right? Because it is very aggressively turning upwards, which means the centripetal force is upwards, right? And so in this case, the airplane has to provide a lift that is not only counteracting gravity upwards, but also providing the centripetal force also upwards. So it needs to create a lot of lift. And as a result, the air has to be propelled in the opposite direction, downwards, right? And here you can clearly see the downwards air kind of impinging on the desert, right? So this is actually a very illustrative scenario for how the air, especially from a macroscopic point of view, right? How the air in the lifting, around the lifting body has to move. And let's actually compare that to this. So this is actually a calculation of a pair of vortices impinging on a wall. So see how similar this is to what the sand is doing, right? In the movie. Let's look at this again. Right, so it is basically essentially doing the same thing. So you probably already learned in Unified, right? There is a pair of tip vortices coming from a finite span wing that, in this case, impinges on the ground. And so here, what we'll start to look at in more detail is that what is the structure of the air motion behind an airplane, and in particular, how much the motion behind the airplane has to be to provide the lifting force required by the airplane, and how much energy is in that motion in the air, right? What I said before is that if I have pure lifting forces with no drag, not even induced drag, then there is no energy that's left behind the lifting body. But for an airplane to create lift, especially a high lift, it has to move air downwards. And the energy it leaves behind it is not just proportional to the lifting force, but proportional to the lifting force to what power? Like the momentum exchange between the airplane and the air requires that for the same velocity, right? If I have to double my lift force, the air movement, the velocity of the air behind the airplane has to double, actually, right? The velocity has to double. And therefore the energy content, the kinetic energy, has to quadruple. It's the velocity square. Right, so that is why for the induced drag for an airplane that generates only a little bit of a lift is negligible. But the more the lift it generates, right, the induced drag goes like square of the lift. It's exactly because of the relation between momentum and kinetic energy behind the airplane. And so we'll look into a lot more in detail of the flow structure behind it, and that is actually driven by the dynamics of vortices. Now, before we look into that, right, we looked at in the last lecture about the magnitude of the aerodynamic forces, which is we analyzed, okay, the delta momentum, okay, is proportional to v squared, right, and therefore the aerodynamic forces are proportional to v squared. So let's actually take this specific scenario and the airplane kind of lifting away from its flat trajectory, providing the lift providing a huge centripetal force. So I'd like you to maybe work in pairs. Let's like group into pairs and work out roughly what is the mass of the air set in motion by Maverick's airplane in 1 second. And assuming the air is set to move downward at, I said 1% here, but like let's say X% of the speed of his airplane. how much lift does the airplane generate. And the variables you can use is the speed of the airplane, wingspan, and the air density. Now the critical question here, you have to work out is how much air is moved by the airplane. And we'll see that what you can use in your unified study, and basically it requires some approximation, and to your best judgment, figure out how much air is set in motion by Maverick's airplane in 1 second. All right? Okay, let's group into pairs and start to work on answering the question.
I'm immediately drawn to a control volume.
I mean, we have what we did last time, volume are affected by the
How much downstream momentum? We're trying to find the mass of the air. So if we find the change in momentum, we can find.
yeah.
Momentum is conserved, and then we.
Why don't we work together?
Yeah, one side is like plane momentum, the other is air.
The velocity of the airplane. But this was assuming the air behind the separated wing moves with the wing. But in this case, we care about the air down.
So I guess if we're looking at
Also change.
Right, so you basically need to calculate, so the air setting downward is like the genuine that.
If we just do the MV equals MV, I think we already have the V of the air, right? That's the 1%. Then we can just make an approximation for the mass of.
And you can calculate
And we
can come up with and changing the momentum is a kilogram the weight.
I mean,
Force is basically how much
you can calculate the weight air.
Right, because in order for
Times some factor, right? Because it's
in order for the plane to fly, we're changing the momentum of the air. The momentum of the air.
we already have half of it because we know the speed of it.
Right. We know the velocity, we know the density, and we just need to know E and T, which is
into a delta.
We have
speed.
yeah.
You want
So we need to know the air momentum
We want to find the mass of air second.
yeah, right, so per second.
As if we look at it from the side like a 2D view, I don't think we need it.
So
you don't think so?
so this is basically
Unless we're doing like a 3D boss.
which is like
Well, it required
b squared over.
I'm looking.
Oh, I'm stupid. I'm stupid. Span is not 4.
That is an acceleration.
Yeah, I still think we need
Or maybe it does cancel out in the end, like with find the mass, we need density and the volume.
Yeah, so this is mass of the plane.
Any questions you have, or any?
Like we could try to introduce it in and see if it disappears.
I think we have a path.
Okay, yeah, we have something. So if we want this, these times on velocity of the plane, we need to estimate the mass of the plane and gravity plus these we don't know. Well, all of these we have to estimate.
Okay. Yeah. So if you think alternatively from the air's perspective, right? Not just from the airplane's perspective, right? How much? So what you are looking at is how much force does the airplane has.
Yeah, but the only way of getting that force is by pushing air down.
Yes.
So, like, if you draw momentum on the airplane, so every momentum that goes up with the airplane has to go down.
Exactly. Yes.
That's it. So
yeah. So the critical thing is to figure out how much air is set in motion. Right? How much air does the airplane download? Right? There's no CP. Right? So if you look at this blob of air, right, before the airplane passes, it's just sitting there. Right? After the airplane passes, it's now going down. Right? Yeah. How much of that air?
So I mean, I can rearrange it to get mass over time, right? And this is just the percent speed difference, right? And then we have the mass speed difference. Yeah, the velocity of the plane is
In 1 second.
it moves downward at 1%.
Oh.
Yeah, exactly. So we have to basically rewrite the mass of the plane in terms of the speed and wingspan.
It's an effective. The air is 14,000.
Well,
downstream flow field is
yeah, I mean that's not wrong, but I feel like we should use I mean, that's what I would mean.
We don't have.
Oh, that's the right one.
Can we use the DL equation?
So
I
if
don't
we
think
do a sub,
we have span and
Yeah.
density, but
We did like here.
yeah,
Oh, right.
I mean, it's some proportionality. There's some proportionality, and then the force.
we have 3 of those.
But I guess we could do.
We could just make up a coefficient of lift.
I mean, you can-
same way we did up the mass of the airplane.
Or we could just say CL.
Okay. Yeah.
We could divide by 4. Do massive air per second.
Yeah, why is it always?
Oh, you plugged in a number for me. I just need to be.
Why does this matter for us? That's what I don't get it. Like it should be.
Okay, I see a lot of very good progress. So one thing I want to, a lot of question I want to answer here is that there was a very good question, right? Can you use the chord length in the answer? The reason people wants to use chord length is to figure out how much air is moved by the airplane, right, downstream. And my answer is no, you're not allowed to use C. Why? The reason is that if you zoom out, if you look several spans after the airplane passes, like what's happening over here, the flow field is dominated by 2 vortices, right? And actually, the location of the vortices has nothing to do with C, right? And from unified, what is the flow field induced by the vortices? You may not remember the formulas, but I hope you still qualitatively understand what the flow field around a vortex looks like. And you can just add up the flow two vertical flow fields to have a velocity field like that, right? So away from the vortices, the flow velocity is going to be smaller, and near the vortices, the flow field is going to be stronger, right? So if you think about the area over which the flow has a significant velocity, that area probably looks something like that, something like a circular or elliptical region. That the size, both the height and width, is some constant times the span-wise distance between the 2 vortices, which is roughly the span, right? So basically, both the height and width of the air that's significantly moved by the airplane is proportional to the span. You don't need to use the chord. Okay? Okay, keep going.
That makes a lot more sense, actually. Because why would you try to bigger effects?
Yeah.
There would be more lift, right? Which would theoretically mean the air is moving faster. More air is moving faster.
air is moving faster, but not more air is moving.
Well, either that or more air is moving at the same speed.
Yeah.
Right. But I mean, I can see how this would be.
Interesting. But I don't remember. What about like adding the vortices?
I mean, what there's the equation for the speed of the air some distance away. And I think if we say at like half the span, so right in the middle between the two, if we add the two, it should be 1% over v.
Right.
Right? So then we can find the strength of the vortices that way.
Yeah. I just don't remember exactly the formula. Here it is.
Yeah, I want to know the acceleration of the velocity.
How are you trying to use that?
So that is 1% of the
Acceleration.
So slightly over 100.
Oh.
But I think, I don't know. Because we obviously don't know.
Okay, very nice. I see several groups already got the answer. Can somebody tell me what is the mass of the air set in motion per second? Anybody? Yes?
Rho v squared times v.
What?
Rho times v squared
times v, right? Yeah, so there is it's actually proportional to this because b squared is going to be like this square over here, right? This region is going to be proportional. So that's very good. That's how much air is set in motion significantly, right, per second. Now let's say let's just take this 1% as an example. What is going to be the lift generated by moving this much air per second? Yes? Anybody? It is just the mass per second times the delta V, right? The mass flux times delta V is going to be the force. Okay, that's again, it's exactly the same in aerodynamics versus rocketry, right? It's just again, a rocket manipulates fluid by brute force, and the aerodynamics manipulates fluid in much more clever ways. Okay, so basically the force is going to be proportional to rho b squared times v squared times this 1%. All right, the constant, the proportionality constant should be order 1. All right, any questions on that? Yes?
I still didn't get why the v squared.
Oh, why the v squared? Because so this is the mass per second that already has a v, right? And the force is equal to mass per second times delta v. So mass per second is equal to this, right? This is mass per second, and the delta v is equal to 1% times the velocity of the airplane. So the v actually appears in 2 places multiplied together.
No, I mean the b squared, like the span.
Oh, why the b squared? Oh, sorry. Okay, the reason that the amount of air is proportional to b squared is because the flow field is dominated by the 2 vortices. And so that's something we'll analyze in a bit more detail later. But the flow field around the vortex is actually something we'll explain in detail next Monday. Okay, so this b squared is just a approximation that comes from maybe what you learned from Unified, that the velocity around the vortex, right, is equal to basically Vx is going to be gamma over the distance between basically y minus y0. So basically the x velocity is inversely proportional to well, actually it is not just that, it is actually the r squared times the r squared x times y, right? And Vy is going to be minus gamma times x over r squared. So that's basically how the flow field around the vortex looks like. First of all, it's rotational in the sense that the x velocity is proportional to y and y velocity is proportional to minus x. That makes the flow field exactly rotational. And then the magnitude of the velocity is, I think there is a 2 pi if we look at here. The magnitude of the velocity is inversely proportional to the distance between the center of the vortex and the location of the flow field, right? Both these added together makes it that the region with a significant velocity is going to be proportional to both the height and the width is proportional to the distance between the two vortices. All right, so that's something we'll look more analytically next week. And in particular, we'll look at induced drag, for example, and how induced drag depends on not just the distance between the two vortices, but also the distribution of vorticity along the span. All right, so that's going to be taking a more calculus and analytical approach. Okay, so finally, let's actually look at how much energy does it cost to generate lift. All right, so we have already seen that the force it takes is equal to mass per second times delta V, right? So the energy it takes to move that amount of air is equal to what? Is equal to still the amount of mass, the amount of air mass is moved per second times what? Times not the delta V, but specific, yes, half of delta V squared, right? So that makes it a very interesting thing, because in order to generate the same amount of lift force with less energy, which of the two terms do you want to make it large? Which of the two terms do you want to make it small? Right? If you want the same force, that means the product of the mass per second and the delta V has to be the same. Increasing which term, decreasing which term is going to reduce your energy consumption. Yeah. Increase the amount of mass and decrease in the delta V, right, is going to make it a lot more efficient. Right, that's the most intuitive explanation for why, if you want a high energy efficient lifting device, you want to move a lot of mass per second, which means a large span, right? Because the mass we are moving per second is proportional to the square of the span. And that actually reduces how much delta V you have to move the air, and therefore reduces how much energy you have to spend in generating the same lift. Yes?
Is this the same principle as like high bypass engines?
Yes, it's the same principle as high bypass engines, exactly the same, right? So you want to move a large amount of air with less velocity, except for in high bypass engines, the second term doesn't exactly look like that, because you have to, like, the energy the energy is a little bit different, but like it's the same principle, right? Yes.
If you have a fixed span and you want to move more mass, it seems like you'd want to increase the chord, but that would decrease the aspect ratio, which would make it less efficient. So is there a trade-off there? Or is that just two completely separate effects?
Yeah, the question is, if you want to move more air for the same span, it sounds like you want to increase your chord, right? And that's actually not the case. So no matter what your chord length is going to be, the air movement behind the airplane actually has exactly the same pattern if the lift per span is actually exactly the same. The chord length actually does not affect significantly the airflow after the airplane. The longer after the airplane you look at, the less it impacts.
So if you want to move more mass, you would want to increase the velocity of the plane.
Yes, another way to increase the mass per second is to increase the velocity of the airplane, right? That is why for a slow-moving airplane like a glider, you really want to have a very large span. For a faster-moving airplane, it's less important. All right. So very good point. Yes.
Having a thicker chord length is more so just so the wing doesn't break or something.
Have a thicker chord length actually, have a bigger chord length actually is most important when you are taking off a landing, right? Because as we are going to look at in the viscous flow section, you can't generate infinite lift with a finite chord length, right? So there is a maximum lift you can generate, and beyond that, you're going to stall. So having a large chord actually helps to take off and land most significantly. Okay, finally, let's. We don't have time to look at this, but we are going to have another homework that's looking at a bird. So it's really remarkable that this bird actually, during its entire lifespan, it flies the equivalent of a round trip from Earth to the Moon more than 3 times. It's probably the kind of animal that goes the furthest away during its lifetime. And we'll look at how much energy does the bird spend during its lifetime moving air downward versus dragging air along with it. All right. And we'll actually quantify that in terms of gallons of fuel and see how much energy does the bird spend traveling that much distance. So, okay, so I'll see you in the wind tunnel tour in the afternoon.
Yeah, one.